Between two dying galaxies, something impossible is being born. A black hole 1 million times the mass of our Sun appeared where no black hole should exist. It floats in the void between colliding worlds, feeding on a glowing bridge of hydrogen gas. We thought black holes needed billions of years to grow this massive. We were wrong. The James Webb Space Telescope just found evidence of direct collapse, a cosmic shortcut that breaks every rule. If you're ready to see the universe rewrite its own laws, hit that subscribe button. What we discovered changes everything. Let's begin. Two galaxies are tearing each other apart billions of light years from Earth, and their death dance created something astronomers had never seen before. When researchers Pieter van Dokkum and Gabriel Brammer were scanning through archived images from the James Webb Space Telescope, they stopped cold. There on their screens sat a shape that shouldn't exist in nature. A perfect figure 8, an infinity symbol blazing in the cosmic dark. The image shows two brilliant red cores, each wrapped in glowing rings of stars. They mirror each other like cosmic twins frozen in time. Between them stretches a bridge of bright green light, hydrogen gas stripped down to its bare atomic bones. This is the Infinity Galaxy. Scientists confirmed it formed when two massive spiral galaxies slammed into each other head-on, a collision so violent it reshaped everything. But here's what makes this discovery stranger than the shape itself. That green bridge of gas is glowing for a reason. Something in the middle is eating it, something that wasn't supposed to be there. The two galaxies collided with such force that their stars got flung outward into rings, while their gas clouds smashed together in the center. Think of two water balloons hitting each other at high speed. The rubber flies apart, but the water crashes together in a single explosive burst. That's what happened here, except the water is 1 trillion times the mass of our Sun, and the explosion is still happening. Webb's infrared camera can see through the cosmic dust that hides these collisions from regular telescopes. The image reveals details invisible to human eyes. The twin cores glow red because they're packed with older stars. The rings shine with young blue stars born from the chaos. And that green glow, that's hydrogen being ripped apart by something with immense gravity. The team nicknamed it the Infinity Galaxy because of the shape, but the name carries extra weight now. This collision might have created something that could exist forever, something that can never be destroyed, a black hole. Galaxy collisions happen throughout the universe. They're not rare, but this collision revealed a cosmic recipe that scientists have been hunting for decades. The exact conditions needed to birth a monster. Nobody expected to find what came next. When the team looked closer at that glowing green bridge, they found signatures of intense radiation, X-rays, radio waves, the telltale signs of a supermassive black hole actively feeding, growing. But supermassive black holes live at the centers of galaxies. They're the anchors around which everything else orbits. This one was floating in between. The discovery triggered an immediate puzzle. How did a black hole weighing 1 million times the mass of our Sun end up in the middle of nowhere? Did it get ejected from one of the colliding galaxies? Did it wander in from somewhere else? Or did something far stranger happen here? The answer would force scientists to reconsider everything they thought they knew about how black holes form. But first, they had to prove this black hole wasn't supposed to be where they found it. Black holes don't float around in empty space like cosmic tumbleweeds. They sit at the hearts of galaxies, trapped there by gravity since the universe was young. Every major galaxy ever studied has one at its core. The Milky Way has Sagittarius A star, 4 million times the Sun's mass. Andromeda hosts one even bigger. They're galactic anchors, not wanderers. So when Van Dokkum's team confirmed a supermassive black hole sitting between the two cores of the Infinity Galaxy, the astronomy community erupted with questions. This wasn't a small stellar black hole drifting through space. Those exist and they're manageable mysteries. This was a giant, a beast that should be locked in place by the gravity of billions of stars. The black hole sits exactly in the middle of that green hydrogen bridge, not near one galaxy or the other, dead center, like someone carefully placed it there on purpose. The team measured its position dozens of times to be sure. Every measurement confirmed the same impossible fact. 3 possibilities emerged immediately. Maybe the black hole got ejected from one of the colliding galaxies during the crash. Supermassive black holes can get kicked out of their homes during violent galaxy mergers. It's rare but possible. Computer simulations show that when 2 galaxies merge, their central black holes eventually spiral together. During that death spiral, they can throw each other around like cosmic wrestlers. But ejected black holes travel at extreme speeds. They race through space at thousands of miles per second, fleeing their birthplace like cosmic bullets. If this black hole had been thrown out, it should be moving fast relative to everything around it. The second possibility seemed even stranger. Maybe a third galaxy sits directly behind the infinity galaxy from our perspective. A hidden galaxy that just happens to line up perfectly with the collision zone. Its central black hole would appear to sit between the 2 main galaxies, even though it's actually much farther away, a cosmic illusion. This kind of alignment happens sometimes in astronomy. It's called a chance superposition, like seeing 2 stars that appear right next to each other in the sky, but are actually separated by trillions of miles. Perspective tricks are common in space. The third possibility made Van Dokken pause. What if the black hole didn't come from anywhere else? What if it formed right there, in that bridge of gas, during the collision itself? This option violated everything in the textbooks. Black holes don't spontaneously appear in clouds of gas. They need something to collapse, usually a massive star. Stars live for millions or billions of years, then die in supernovas that leave black holes behind. That's the standard story. The only story anyone could prove. But there's a theory, whispered about in research papers for years, that suggests another way, a shortcut. Under perfect conditions, a massive cloud of gas could skip the star phase entirely and collapse straight into a black hole. Scientists call it direct collapse. They've never seen it happen. Until now, it remained purely theoretical. The team knew they needed proof. They needed to measure how fast the black hole was moving compared to the gas around it. If it was racing through at high speed, that would support the ejection theory. If it sat motionless, perfectly embedded in the gas cloud like a spider in its web, that would suggest something far more revolutionary. They applied for more telescope time. The waiting began. But while they waited, they started calculating exactly how massive this mystery black hole really was. The numbers would shock them. The black hole weighs as much as 1 million suns crammed into a space smaller than our solar system. Let that sink in. 1 million stars like ours, compressed into a region where gravity becomes so intense that nothing, not even light, can escape. The team calculated this mass using multiple methods, and every calculation pointed to the same staggering number. To understand how absurd this is, you need to know how black holes normally grow. They start small. A typical stellar black hole, born from a dying star, weighs maybe 10 to 100 times the mass of the Sunday. That's the seed. From there, it grows by eating. Gas falls in. Dust spirals down. Maybe it merges with another black hole during a galaxy collision. The process takes time, billions of years. Astronomers have a formula for how fast black holes can grow. It's called the Eddington limit. As material falls into a black hole, it heats up and releases radiation. That radiation pushes back against the infalling matter like a strong wind. There's a maximum rate at which a black hole can feed before its own light pressure stops more food from falling in. Even feeding at that maximum rate constantly, a 10 solar mass black hole would need billions of years to reach 1 million solar masses. The universe is 13.8 billion years old. That gives plenty of time for black holes to bulk up. But here's the problem. The James Webb Space Telescope keeps finding supermassive black holes in the early universe. Black holes with billions of solar masses existing when the cosmos was less than 1 billion years old. Some appeared just 500 million years after the Big Bang. The math doesn't work. There simply wasn't enough time for small stellar black holes to grow that massive, even if they fed at the maximum rate non-stop. It's like finding a full-grown oak tree in a forest that was planted yesterday. Something's wrong with our story. The Infinity Galaxy black hole weighs 1 million solar masses, sitting in a collision zone that likely formed relatively recently in cosmic terms. The two galaxies smashed together billions of years ago, yes, but compared to the age of the universe, this collision is recent. There's no nearby star dense enough to have died and left behind a black hole this massive. This mass sits in a specific category that makes scientists uncomfortable. It's too big to come from a single star, too small to be an ancient galaxy core black hole. It's exactly the size that direct collapse theory predicts for a newborn supermassive black hole. When gas clouds collapse directly without forming stars first, the theory suggests they create black holes between 100,000 and 1 million solar masses. Heavy seeds, scientists call them. Born big, born fast, ready to grow into the giants we see powering ancient quasars. The team stared at their mass calculations. 1 million solar masses sitting in a gas cloud between colliding galaxies. The number fit direct collapse predictions perfectly, too perfectly to be coincidence. But mass alone doesn't prove anything. Plenty of black holes reach 1 million solar masses through normal growth. What made this one special wasn't just its weight, it was where that weight existed. And whether that weight was moving or stationary, the velocity measurements would arrive soon. Until then, the team turned their attention to the glowing green gas surrounding this cosmic beast. That hydrogen glow held secrets of its own, secrets that would confirm their wildest suspicions. The green light stretching between the galaxy cores isn't just pretty inward, forming a disk around the black hole called an accretion disk. Friction in that disk heats the gas to millions of degrees. That superheated gas screams out radiation across the spectrum. Ultraviolet, X-rays, radio waves. That radiation slams into the surrounding hydrogen gas, ripping electrons away from their atoms. The atoms don't stay ionized forever. Eventually, they recapture electrons, and when they do, they release light at specific wavelengths. Webb's camera detects that light as green in false color images. The green glow maps exactly where the black hole's radiation reaches. The team measured the size of the ionized region. It extends across thousands of light years, a vast swath of space lit up by the feeding black hole. This isn't a small effect. This is industrial-scale cosmic violence. The black hole is actively accreting matter right now, pulling in gas from the surrounding cloud and converting that matter into the most intense radiation in the universe. But here's what made the scientists lean forward in their chairs. The ionized gas isn't concentrated around either of the two galaxy cores. It's concentrated between them. The brightest, most intense ionization sits right where the black hole lurks. Like a spotlight on a stage, the green glow illuminates the exact location of the hidden monster. Van Dokkum's team combined Webb's infrared data with observations from other telescopes. The Chandra X-ray Observatory detected hard X-rays coming from the same location. X-rays are smoking gun evidence of black hole accretion. Only black holes and neutron stars produce X-rays with those energies, and neutron stars are far too small to generate this much power. The Very Large Array, a massive network of radio telescopes in New Mexico, picked up radio emissions from the same spot. Black holes launch jets of particles at nearly the speed of light when they feed. Those jets emit radio waves. The radio signal confirmed that something with tremendous mass and energy sat in that hydrogen bridge. 3 independent telescopes, observing in 3 different types of light, all pointing at the same cosmic address, all seeing the signature of an actively feeding supermassive black hole, not near the galaxies, not hiding behind them, right in the middle where it had no business existing. The ionized hydrogen revealed something else crucial. The team could measure how the gas was moving. Ionized atoms emit light at specific wavelengths, but if those atoms are moving toward or away from us, the wavelengths shift slightly. It's called the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it drives past. By measuring these wavelength shifts, astronomers can determine how fast gas is moving and in what direction. The team analyzed the ionized hydrogen throughout the bridge. They found it swirling, turbulent, chaotic. The collision had stirred this gas into violent motion. Shock waves rippled through it. Pressures and temperatures fluctuated wildly. This chaos mattered. This turbulence would become central to their argument. But first, they needed to measure the black hole's velocity and compare it to the gas. That measurement would arrive within weeks. Until then, they documented every detail of the green glow, every nuance of the ionization pattern. The glow proved a black hole was there. The velocity would prove how it got there. The difference between those two facts would rewrite textbooks. For decades, scientists believed they understood how supermassive black holes formed. The story seemed simple and logical. Stars die, black holes are born, and those black holes grow slowly over cosmic time. This is called the light seed theory, and until recently, nobody seriously questioned it. The evidence seemed solid. Here's how it works. The universe's first stars formed roughly 200 million years after the Big Bang. These weren't stars like our Sunday. They were monsters, some weighing 100 to 300 times the sun's mass. They burned hot and fast, exhausting their fuel in just a few million years. When they died, they collapsed into black holes. These first stellar black holes weighed between 10 and 100 solar masses, small by cosmic standards, but they were seeds. Given enough time and food, they could grow. Gas clouds drifted nearby. Dust accumulated. The black holes pulled matter in, gaining weight like cosmic bodybuilders. When two galaxies merged, their central black holes eventually found each other. They spiraled together over millions of years, then merged in a catastrophic collision that sent gravitational waves rippling across space. The merger created a larger black hole. Two 100 solar mass black holes become one 200 solar mass black hole. Simple addition. This process repeated throughout cosmic history. Merge, eat, merge, eat. Over billions of years, the light seeds grew into supermassive black holes weighing millions or billions of solar masses. They took up residence at the centers of galaxies, growing alongside their hosts. Galaxy and black hole evolved together, locked in a cosmic partnership. The theory made sense. It matched observations in the nearby universe. It explained why bigger galaxies tend to have bigger black holes. It fit the timeline. Everything worked. Until James Webb started looking at the early universe. Webb's infrared vision can peer back through cosmic time to when the universe was young. The telescope detected galaxies that formed just a few 100 million years after the Big Bang. And in the centers of many of these infant galaxies, blazing brightly, sat supermassive black holes with billions of solar masses. The astronomers ran the numbers again and again. They checked their calculations. They verified their measurements. The conclusion remained unavoidable. These black holes were too massive, too early. Starting with a 10 solar mass seed, feeding at the maximum Eddington rate without pause, a black hole might reach 1,000 solar masses after 100 million years. After 500 million years, maybe 10,000 solar masses. To reach 1 billion solar masses would take at least 1 billion years of continuous maximum rate feeding. But Webb found billion solar mass black holes when the universe was only 500 to 800 million years old. The light seed theory can't explain them. There simply wasn't enough time. Even if every condition was perfect, even if these black holes never stopped eating for 1 second, they couldn't have grown that large that fast. Some scientists tried to salvage the theory. Maybe black holes could exceed the Eddington limit under special conditions. Maybe they fed faster than we thought possible. Maybe the first stars were even more massive than simulations predicted, creating bigger seed black holes. The modifications helped a little, but the timeline still didn't work. The numbers refused to add up. The light seed theory wasn't wrong exactly. It described how many black holes grow, but it couldn't explain the giants Webb kept finding. Something else had to be happening in the early universe. A different path, a shortcut. Scientists needed a way to create massive black holes quickly, without waiting billions of years for slow growth and mergers. They needed heavy seeds, and that led them to one of the most controversial ideas in astrophysics. The James Webb Space Telescope has become a problem-making machine, and the astronomy community is scrambling to keep up. Every few months, Webb spots another supermassive black hole that shouldn't exist yet. Ancient quasars blazing in the cosmic dawn. Black holes powering galaxies when those galaxies were barely formed. Monsters that broke the growth takes time. But these early universe black holes don't have time. They exist during cosmic infancy, yet they've already reached adulthood. It's like finding a blue whale swimming in an ocean that was created yesterday. Scientists tried every workaround they could imagine. Maybe seed black holes started bigger than we thought. Maybe the first stars were absolute giants, creating black holes hundreds of times the sun's mass instead of just tens. That helps, but not enough. Starting with 100 solar mass seed instead of a 10 solar mass seed only buys you a little extra time. You still can't reach billions of solar masses in 500 or 600 million years. Maybe black holes fed faster. Maybe they exceeded the Eddington limit by a factor of 10 or even 100. Super Eddington accretion does happen in extreme circumstances. But maintaining that feeding rate continuously for hundreds of millions of years seems physically impossible. The radiation pressure should blow away the surrounding gas, cutting off the food supply. Maybe black holes merged more frequently than simulations predict. Every merger instantly doubles the mass, skipping the slow eating process. But galaxy mergers take time to complete. Black holes need millions of years to spiral together after their host galaxies collide. You can't pack enough mergers into the early universe timeline to explain these giants. Every solution creates new problems. Every patch in the theory opens another hole. The light seed model, which worked beautifully for nearby modern black holes, fails spectacularly when applied to the early universe. Something fundamental is wrong with our understanding. The paradox frustrated scientists for years. Conferences featured heated debates. Research papers proposed increasingly exotic solutions. Some scientists suggested we needed to modify general relativity itself. Others argued that our cosmological timeline must be wrong. Maybe the universe is older than we calculated. Maybe the laws of physics behaved differently in the early cosmos. But most scientists suspected a simpler answer. Maybe black holes had two different formation pathways. The light seed path works fine for typical black holes. It explains the millions of stellar mass black holes scattered through galaxies. It accounts for the supermassive black holes in modern galaxies that had billions of years to grow. But for the early universe giants, maybe nature found a shortcut. Maybe under special conditions, gas clouds could collapse directly into massive black holes without forming stars first. No waiting for stellar death, no slow accumulation, just rapid gravitational collapse, creating a black hole weighing 100,000 to 1 million solar masses right from the start. These heavy seeds could then grow to billions of solar masses in the time available. Starting big means reaching giant size faster. The math works if you begin with 1 million solar mass seed instead of a 10 solar mass seed. The timeline fits. The problem? Nobody had ever seen it happen. Direct collapse remained theoretical, a mathematical possibility that might occur in computer simulations but had never been confirmed in the real universe. Scientists needed evidence. They needed to catch a heavy seed in the act of forming. The Infinity Galaxy might finally provide that evidence. But first, scientists needed to understand what prevents gas clouds from forming stars. Imagine trying to build a cathedral in a single day. That's essentially what early universe black holes accomplished. They reached sizes that should require billions of years of construction, but existed when the universe was less than 1 billion years old. The math becomes clearer when you break down exactly how long black hole growth takes. A black hole grows by pulling in matter. Gas spirals inward through an accretion disk, gradually crossing the point of no return called the event horizon. Once matter crosses that boundary, it's gone forever, added to the black hole's mass. Simple enough in principle, but physics imposes strict limits on how fast this process can happen. The Eddington limit defines the maximum rate at which a black hole can accrete matter. As gas falls inward, friction heats it to millions of degrees. That hot gas radiates enormous amounts of light. The outward radiation pressure pushes against the infalling gas. At some point, the outward push exactly balances the inward gravitational pull. That balance point is the Eddington limit. For a 10 solar mass black hole, the Eddington limit allows it to roughly double its mass every 45 million years. Sounds fast, right? But watch what happens when you run the timeline. After 45 million years, you have 20 solar masses. After 90 million years, 40 solar masses. After 135 million years, 80 solar masses. After 1 billion years of feeding continuously at the Eddington limit, starting from 10 solar masses, you reach about 30 million solar masses. That's impressive growth, but it's nowhere near the billion solar mass monsters Webb keeps finding. Not even close. You'd need roughly 5 billion years to reach 1 billion solar masses, starting from a 10 solar mass seed. Scientists ran thousands of simulations trying to find a way around this timeline. Maybe if seed black holes started larger, say 100 solar masses instead of 10, they could reach bigger sizes faster. But that only gains you one doubling time. You still can't reach billions of solar masses in 600 million years. Maybe black holes fed at 10 times the Eddington limit. Super Eddington accretion does occur in nature. Some black holes manage to pull in gas faster than the radiation pressure can push it away, especially if the gas falls in from many directions at once. But maintaining super Eddington accretion for hundreds of millions of years seems physically implausible. The system should stabilize back to normal. Eddington limited feeding relatively quickly. Maybe the early universe had more available gas for black holes to eat. True, galaxies were more gas-rich back then, but more available food doesn't mean the black hole can eat faster. The Eddington limit depends on the black hole's mass and the physics of radiation pressure, not on how much food sits nearby waiting to be consumed. Every attempted solution hit a wall. The timeline remained stubbornly wrong. Black holes simply cannot grow from stellar mass seeds to billions of solar masses in the time available, not through accretion, not through mergers, not through any combination of normal processes. The time crunch forced scientists to consider alternatives. If black holes can't grow from small seeds to giant sizes fast enough, maybe they don't start small. Maybe they start big. Heavy seeds weighing 100,000 to 1 million solar masses would have a massive head start. Beginning with a million solar mass seed, reaching 1 billion solar masses takes less than 500 million years of Eddington limited feeding. The numbers work. The timeline fits. Heavy seeds solve the paradox elegantly. But how do you create a million solar mass black hole without stellar death and slow growth? You need a completely different formation mechanism. You need direct collapse, and you need to solve one massive problem. Gas clouds naturally form stars, not black holes. Direct collapse offers an elegant solution to the early universe paradox. Instead of starting with a small stellar mass black hole and waiting billions of years for it to grow, nature could skip ahead. Under perfect conditions, a massive cloud of gas might collapse directly into a black hole, weighing 100,000 to 1 million solar masses. No star formation, no supernova. Just pure gravitational collapse, creating a heavy seed in one catastrophic event. The physics is straightforward. Take a gas cloud weighing millions of times the sun's mass. Make it dense enough. Make it massive enough. Gravity will eventually overwhelm all other forces and crush the cloud into a black hole. It's the same process that forms stars, just taken to an extreme endpoint. When a normal gas cloud collapses, it fragments into thousands or millions of pieces. Each piece becomes a star. The cloud doesn't stay together as one object. It breaks apart because cooling and turbulence create density variations. Dense spots collapse faster, pulling matter away from less dense regions. The result is a cluster of stars, not a single massive object. But change the conditions slightly, and the story changes. If you prevent the gas from cooling efficiently, it stays hot. Hot gas has more pressure. More pressure resists fragmentation. The cloud can collapse as a single coherent mass instead of breaking into pieces. If the collapse proceeds fast enough, the center of the gas cloud reaches densities and temperatures where quantum physics and general relativity take over. At densities around 10 million grams per cubic centimeter and temperatures of 10 billion degrees, the gas undergoes what scientists call a general relativistic instability. The object becomes its own worst enemy. Its gravity becomes so intense that it can no longer support itself against further collapse. At that point, nothing can stop the process. The core of the gas cloud collapses catastrophically. Space itself warps and curves under the extreme gravity. Within minutes or hours, an event horizon forms. A black hole is born. This newborn black hole weighs 100,000 to 1 million solar masses right from its first moment of existence. That heavy seed can then begin normal accretion, growing at the Eddington limit like any other black hole, but it starts with a massive advantage. Beginning with 1 million solar masses instead of 10 solar masses means reaching billions of solar masses becomes possible within the early universe timeline. The time crunch disappears. Computer simulations show that direct collapse can work in principle. Scientists have run detailed models of gas clouds collapsing under idealized conditions. The simulations produce heavy seed black holes matching the predicted mass range. The physics checks out. The math works. Direct collapse is possible. But possible doesn't mean common. It doesn't even mean it actually happens in the real universe. Simulations make assumptions and simplifications. They model perfect conditions. Nature is messy and complicated. Just because a process works on a computer doesn't guarantee it occurs in reality. Scientists needed to find a direct collapse black hole in the wild. They needed to catch one in the act of forming, or find one so young that it clearly couldn't have formed through normal stellar evolution. They needed evidence beyond theory and simulation. The search focused on the early universe. If direct collapse occurred anywhere, it would be in the first billion years of cosmic history. That's when conditions were right. That's when the universe needed heavy seeds to explain the supermassive black holes Webb keeps finding. Researchers identified a few candidate objects that might be direct collapse black holes. Some X-ray sources in distant galaxies had properties consistent with heavy seeds, but the evidence remained ambiguous. The observations could be explained by other phenomena. Nothing definitive emerged until the Infinity Galaxy, until two colliding galaxies created a laboratory for direct collapse right where telescopes could study it, until a black hole appeared between galaxy cores in a location that demanded explanation. But there's still a problem, a fundamental problem that applies to all direct collapse scenarios. Gas clouds like to form stars. Understanding why gas sometimes doesn't form stars became the key to the entire mystery. Gas clouds are star factories. Put enough gas in one place and stars are born. It's one of the most reliable processes in the universe. Gravity pulls gas together, the cloud collapses and heats up, and eventually nuclear fusion ignites. A star lights up. This happens constantly throughout every galaxy. Star formation is natural, inevitable, and extremely difficult to prevent. That creates a huge problem for direct collapse theory. If you want a gas cloud to collapse into a black hole instead of forming stars, you need to stop star formation completely. The cloud must stay together as one massive object. It cannot fragment into thousands of pieces. A single fragmentation ruins everything. One newborn star can trigger a cascade of star formation that consumes the entire gas cloud. So what prevents fragmentation? What keeps a gas cloud coherent during collapse? The answer involves molecular hydrogen, one of the simplest molecules in the universe. Two hydrogen atoms bonded together. But this simple molecule controls the fate of collapsing gas clouds. Molecular hydrogen is an extremely efficient cooling agent. When gas clouds collapse, gravitational compression heats them up. That heat creates pressure that resists further collapse. The cloud wants to bounce back like a squeezed spring. But if the gas can cool efficiently, it radiates away that heat. The pressure drops. Collapse continues. Molecular hydrogen cools gas through quantum transitions. The molecule can rotate and vibrate in specific patterns. When it shifts from one pattern to another, it releases a tiny amount of energy as infrared light. That light escapes the cloud, carrying heat away. The gas cools, and cool gas fragments easily. Here's the key insight. If you destroy the molecular hydrogen, the gas can't cool efficiently. Only atomic hydrogen remains, and atomic hydrogen is a terrible cooling agent. Without molecular hydrogen, the collapsing gas stays hot. Hot gas has high pressure. High pressure prevents fragmentation. The cloud collapses as a single mass, so scientists need to find a way to break apart molecular hydrogen. The solution is ultraviolet light in a specific wavelength range called Lyman-Werner radiation. This radiation tears molecular hydrogen molecules apart, splitting them back into individual atoms. It's not quite energetic enough to ionize the atoms, just energetic enough to break the molecular bonds. In the early universe, conditions were perfect. The first stars produced intense Lyman-Werner radiation. That radiation flooded nearby gas clouds, destroying their molecular hydrogen. Those irradiated clouds couldn't cool. They couldn't fragment. They were primed for direct collapse. But there's a catch. The gas clouds need to be pristine, pure hydrogen and helium only. No heavier elements. Elements like carbon, oxygen, and nitrogen are extremely efficient coolants. Just a tiny contamination of these metals allows gas to cool rapidly, even without molecular hydrogen. 1 part in 100,000 is enough to ruin direct collapse conditions. In the early universe, this condition was met. The first generation of stars formed from pure primordial gas. They exploded as supernovas and scattered heavy elements into surrounding space. But some gas clouds remained pristine, protected from metal contamination. Some clouds sat in just the right locations, bathed in Lyman-Werner radiation from nearby galaxies, but shielded from metal-enriched supernova ejecta. Those special clouds could undergo direct collapse. They represented rare environments where all the conditions aligned. Intense ultraviolet radiation, no molecular hydrogen, no metal contamination, massive gas reservoirs. These clouds existed during a brief window in cosmic history when the universe was between 100 and 500 million years old. After that window closed, direct collapse became nearly impossible. Star formation enriched the universe with metals. Gas clouds became contaminated. The conditions for direct collapse vanished as the cosmos aged. Heavy seeds could only form during that brief early period, or so scientists thought. The Infinity Galaxy proved them wrong. It showed that direct collapse might happen in the modern universe under completely different conditions. Not through ultraviolet radiation destroying molecular hydrogen, but through a more violent process. The process of galaxies smashing together at cosmic speeds. Direct collapse needs a perfect recipe, and missing even one ingredient ruins the entire process. Scientists spent years identifying exactly what conditions must align for a gas cloud to collapse into a black hole instead of fragmenting into stars. The list is demanding. Nature rarely checks every box simultaneously. First, you need a massive gas reservoir, not a small cloud, but a behemoth containing millions of times the sun's mass. Bigger is better. More mass means stronger gravity. Stronger gravity means faster collapse. And fast collapse is essential because you can't give the gas time to form stars. The entire process must happen in less than a few 100,000 years. Second, the gas must remain hot throughout the collapse. Temperatures need to stay above 10,000 degrees Kelvin. At lower temperatures, the gas cools and fragments into star-forming clumps, but maintaining high temperatures seems impossible at first glance. Collapsing gas naturally cools as it radiates away energy. Something must continually reheat the gas or prevent it from cooling in the first place. Third, no molecular hydrogen can exist. This molecule cools gas too efficiently. Even small amounts trigger fragmentation. Carbon and oxygen are particularly problematic. Just trace amounts allow the gas to radiate away heat rapidly, dropping the temperature and triggering star formation. Fifth, the gas needs low angular momentum. Rotation resists collapse. A rapidly spinning gas cloud spreads out into a disk instead of collapsing inward. The gas must be falling nearly straight down rather than swirling in circular orbits. This requirement is particularly challenging because most gas clouds in the universe have significant rotation from the turbulent conditions in which they formed. Meeting all 5 conditions simultaneously seems nearly impossible. Scientists calculated that perhaps 1 in 10,000 gas clouds in the early universe satisfied the requirements. Direct collapse black holes should be extremely rare objects, formed only during a narrow window of cosmic history under exceptional circumstances. The early universe offered the best opportunities. Metal-free gas was common. Lyman-Werner radiation from the first stars flooded large volumes of space. Massive gas clouds existed before they fragmented into galaxy structures. The cosmic dark ages created ideal conditions for direct collapse. Scientists expected heavy seeds to form primarily between redshift 30 and redshift 15, roughly 100 to 300 million years after the Big Bang. After that epoch, conditions deteriorated rapidly. Star formation enriched the universe with metals. Supernova explosions scattered heavy elements everywhere. Finding pristine gas clouds became increasingly difficult. The Lyman-Werner radiation background remained strong, but metal contamination poisoned most collapsing clouds. Direct collapse opportunities vanished as the universe aged. Modern galaxies exist in a metal-rich environment. The space between galaxies contains gas enriched to several percent of solar metallicity. Star-forming regions show even higher metal content. Finding the pristine, metal-free gas required for direct collapse seems impossible in the local universe. That's what made the Infinity Galaxy discovery so shocking. Here sat a potential direct collapse black hole, forming not in the early universe, but in relatively recent cosmic time. The collision occurred billions of years ago, yes, but billions of years after the supposed window for direct collapse had closed. The gas should be metal-enriched. The conditions should be wrong. Yet somehow, the collision created the right environment. The violent shockwaves between the colliding galaxies mimicked early universe conditions through a different mechanism. Instead of Lyman-Werner radiation preventing molecular hydrogen formation, turbulence and pressure prevented star formation directly. The collision generated a new pathway to direct collapse, one that doesn't require pristine primordial gas. The team realized they might be watching a formation mechanism that works in any cosmic era. Direct collapse might not be limited to the early universe. After all, 2 spiral galaxies crashed into each other billions of years ago in a cosmic traffic accident that would rewrite black hole physics. They didn't sideswipe each other or merge gradually. They collided head-on, both galaxy disks perfectly aligned, slamming together at speeds exceeding 600,000 miles per hour. The impact released energy equivalent to billions of supernovas. Spiral galaxies are flat disks of stars, gas, and dust rotating around a central core. Imagine 2 dinner plates spinning through space. Now imagine them hitting each other edge first at tremendous velocity. That's what happened here. The galaxies weren't destroyed, they were transformed. The stars in each galaxy passed through each other relatively unscathed. Stars are tiny compared to the vast distances between them. Even in the densest parts of galaxies, stars are separated by light years of empty space. During galaxy collisions, stellar collisions are extremely rare. Most stars sail right through the chaos unharmed. They get flung into new orbits, accelerated by gravitational interactions, but they don't crash. The gas is a completely different story. Gas clouds in each galaxy occupied the same space. They couldn't pass through each other. They collided with tremendous force. The shockwave from that collision compressed the gas to extreme densities. Temperatures spiked into the millions of degrees. Pressure waves rippled outward from the impact zone. That compression launched waves of star formation. The shock compressed diffuse gas into dense clouds, and those clouds immediately began collapsing into stars. Thousands of massive young stars ignited simultaneously, creating brilliant blue regions visible in the Webb image as ring structures. Those rings mark where the density waves triggered violent starbirth. The collision ejected most of each galaxy's stars outward into those ring structures. Conservation of angular momentum flung material away from the impact zone. The two galactic cores, containing the oldest and most tightly bound stars, survived relatively intact. They sit in the ring centers, represented as yellow regions in Webb's image. Between those two cores stretches the collision zone, a bridge of gas caught between the galaxies. This is where conditions became extraordinary. This is where the recipe for direct collapse emerged. The head-on collision generated extreme turbulence in this gas bridge. Shockwaves crisscrossed the region. Gas streams from both galaxies met and mixed violently. Density fluctuations created chaotic pressure variations. The entire zone became a maelstrom of turbulent gas, moving at supersonic velocities. That turbulence prevented normal star formation. Usually, star formation proceeds smoothly. A dense region accumulates more gas through gravity. It fragments into smaller pieces. Each piece collapses and ignites fusion. But in the collision zone, turbulence disrupted this process. Before gas clouds could accumulate and collapse, shockwaves tore them apart. Pressure variations prevented stable fragmentation patterns. The collision also compressed the gas to extraordinary densities. Normal interstellar gas contains about 1 atom per cubic centimeter. That's essentially perfect vacuum by Earth standards. But in the collision zone, densities reached thousands or even millions of atoms per cubic centimeter. That compressed gas had tremendous mass, concentrated in a relatively small volume. High density plus high turbulence equals the perfect conditions for direct collapse. The gas couldn't form stars because turbulence prevented fragmentation. The gas couldn't disperse because density and gravity held it together. The gas could only do one thing. It could continue collapsing under its own weight until something fundamental happened. Something fundamental did happen. Gravity won. The center of that gas bridge reached densities and temperatures where a general relativistic instability triggered. The core collapsed catastrophically. An event horizon formed. A black hole was born between the galaxies. The collision created a modern analog to early universe direct collapse conditions. Instead of Lyman-Werner radiation, preventing molecular hydrogen formation, turbulence directly prevented star formation. Instead of pristine, primordial gas, metal-enriched modern gas collapsed under extreme pressure. The mechanism differed, but the result remained the same. A heavy seed black hole formed in one rapid collapse event. The space between the two colliding galaxies became a pressure cooker operating at cosmic scales. Gas from both galaxies met in the middle, creating a dense bridge of material under extreme compression. Understanding what happened in this zone requires understanding shockwaves and how they transform gas. When two gas clouds collide at high velocity, they don't bounce off each other like billiard balls. They interpenetrate briefly, Then a shockwave forms at the collision interface. Think of two walls of water rushing toward each other. When they meet, the water doesn't reflect backward. It piles up, creating a towering wall where the two streams meet. That's similar to what happened here, except the water is hydrogen gas and the velocity is 600,000 miles per hour. The shockwave compressed the gas to densities far exceeding normal interstellar conditions. Compression heats gas through a process called adiabatic heating. Squeeze gas into a smaller volume and its temperature rises. The collision zone heated to millions of degrees initially. That's hot enough to strip electrons from atoms, creating a plasma. This ionized gas glows brightly, visible as the green bridge in Webb's image. But the temperature doesn't stay constant. Gas radiates away heat through various processes. In normal circumstances, the gas would cool rapidly and form stars. The compression would trigger intense star formation, converting the gas into thousands of new stars within a few million years. But the turbulence changed everything. The collision didn't create a smooth, uniform compression. It generated chaotic, turbulent flows. Eddies and vortices formed at every scale. Gas streams crossed each other at different angles. Density fluctuations appeared and disappeared on timescales of thousands of years. That turbulence injected energy into the gas continuously. Every time gas parcels collided, every time shockwaves crisscrossed the region, they pumped kinetic energy into the system. This energy heating balanced radiative cooling. The gas couldn't cool efficiently because turbulence kept reheating it. The temperature remained high enough to prevent normal star formation. Scientists measure turbulence using a quantity called the Mach number. It compares the velocity of gas flows to the speed of sound in that gas. Mach 1 means gas moving at the sound speed. Mach 2 means twice the sound speed. Supersonic turbulence means Mach numbers above 1. The Infinity Galaxy collision zone exhibits Mach numbers between 5 and 10 based on spectroscopic measurements. That's extremely turbulent. Gas streams are moving 5 to 10 times faster than sound waves can propagate. This supersonic turbulence creates powerful shocks everywhere. The entire region is a network of intersecting shockwaves, constantly processing the gas. This level of turbulence prevents fragmentation through a mechanism scientists call turbulent pressure support. Normally, gravity tries to pull dense regions together while thermal pressure pushes them apart. When gravity wins, the region collapses and forms stars. But add strong turbulence, and you add a third pressure component. Turbulent motions create additional outward pressure that resists gravitational collapse on small scales. Dense clumps trying to form stars get disrupted by turbulent flows. Shockwaves tear them apart. Velocity shears stretch them into filaments. The gas cannot settle into stable star-forming configurations. It remains in a state of violent, chaotic motion, but gravity still works on large scales. The entire gas bridge is gravitationally bound. Even though turbulence prevents small-scale collapse into stars, it doesn't prevent large-scale collapse of the entire structure. The bridge as a whole continues contracting under its own gravity. Mass continues accumulating in the center. This creates the precise conditions needed for direct collapse. A massive gas reservoir collapsing as a single coherent object. High temperatures from compression and turbulent heating. No star formation due to turbulent disruption. All the ingredients assembled in one place. The compression zone measured thousands of light years across, but it contained enough mass to form millions of stars. Instead, all that mass funneled into the center. The density kept rising, the pressure kept building. Something had to give. Eventually, the core reached densities where quantum mechanics and general relativity dictated the outcome. The gas cloud crossed a point of no return. An event horizon formed. The compression zone birthed a black hole. Turbulence in the Infinity Galaxy collision zone operates at a level rarely seen in the universe. It's not gentle stirring. It's violent chaos approaching the theoretical maximum possible in cosmic gas clouds. This extreme turbulence became the key factor preventing star formation and enabling direct collapse. Understanding why requires understanding what turbulence does to gas on different scales. At the largest scales, turbulence mixes material. Gas from one galaxy blends with gas from the other. This mixing homogenizes the composition, spreading metal-enriched gas throughout the collision zone. In a sense, turbulence makes the gas more uniform on large scales, even while creating density fluctuations on small scales. At intermediate scales, turbulence creates filaments and sheets. Gas doesn't stay uniformly distributed. It concentrates into thread-like structures and planar features. These structures constantly shift and evolve. Filaments fragment and reconnect. Sheets ripple and tear. The collision zone resembles a tangled web of gas rather than a smooth cloud. At the smallest scales, turbulence generates eddies and vortices. These are spinning regions of gas, like tiny whirlpools. In normal star-forming regions, these eddies would collapse and form individual stars. But in the collision zone, the turbulent velocity is too high. The eddies tear apart before they can collapse. Every attempt at star formation gets disrupted by the violent motions. Scientists can measure turbulence by looking at spectral line widths. When gas emits light at a specific wavelength, that light gets Doppler shifted by the gas's motion. Gas moving toward us shifts to shorter wavelengths. Gas moving away shifts to longer wavelengths. In a calm region, all the gas moves at similar velocities, so the spectral line is narrow. In a turbulent region, different parts of the gas move at different velocities, so the spectral line broadens significantly. The infinity galaxy collision zone shows spectral lines broadened by velocities exceeding 600 miles per second. For comparison, typical star-forming regions show line broadening of just a few miles per second. The collision zone is roughly 100 times more turbulent than normal star formation sites. That's extreme even by galaxy collision standards. This turbulence must be driven by energy input. Turbulence naturally decays over time as kinetic energy converts to heat through friction and viscosity. For turbulence to persist, something must continuously inject energy. In the collision zone, multiple energy sources feed the turbulence. The ongoing collision provides the primary energy source. The two galaxies haven't finished merging. Gas streams still flow from both galaxies into the collision zone. Every time new gas enters the region, it adds kinetic energy. The collision continues, pumping energy into the system billions of years after the initial impact. Shockwaves provide secondary energy input. Each shock converts organized flow into random, turbulent motion. The collision zone contains countless shocks propagating in different directions. They intersect and interact, creating complex patterns of energy dissipation and turbulence generation. It's a cascade process. Large shocks create smaller shocks. Smaller shocks create turbulent eddies. The system self-sustains its turbulence. Gravity itself contributes. As the gas bridge contracts under its own weight, gravitational potential energy converts to kinetic energy. Material falls inward, accelerating as it goes. This infall motion adds to the turbulent velocity field. Gravity fights to compress the gas, while turbulence fights to disrupt it. The balance between gravity and turbulence determines the outcome. If turbulence dominated completely, the gas bridge would disperse. The random motions would overcome gravity and blow the gas apart. But turbulence doesn't dominate. Gravity is winning the overall battle even though turbulence wins on small scales. This creates a hierarchy. On small scales, turbulence prevents star formation. On large scales, gravity drives continued collapse. The gas bridge contracts as a whole, while remaining too turbulent to fragment into stars. This hierarchy is exactly what direct collapse theory requires. The turbulence also ensures high temperatures. Every shock heats the gas. Every collision between turbulent eddies converts kinetic energy to thermal energy. The gas stays hot, maintaining high pressure. High pressure prevents cooling and fragmentation through an additional mechanism beyond turbulent disruption. Scientists realized this collision created a natural laboratory for testing direct collapse theory. The conditions differ from the early universe scenario, but the essential physics remains the same. Prevent star formation, maintain high temperatures, compress massive amounts of gas into a small volume, let gravity do the rest. The mechanism for preventing star formation differs, but the result is identical. A heavy seed black hole forms through direct collapse. Somewhere in the chaos of the collision zone, at some moment billions of years ago, something crossed a threshold. Gas compressed beyond a critical density. Temperature and pressure reached extremes where normal matter physics breaks down. The laws of general relativity took full control. An event horizon formed. The universe gained a new black hole. This formation event happened quickly by cosmic standards. From the moment the gas cloud reached critical conditions to the moment a black hole existed probably took less than 1 year, maybe as little as a few months. Theoretical models suggest the final collapse proceeds at nearly the speed of light. Once the general relativistic instability triggers, nothing can stop it. The formation sequence follows a specific pattern. First, the gas cloud core reaches densities around 1 million grams per cubic centimeter. That's dense for a gas cloud, but still far below the density of atomic nuclei. At these densities, the gas core becomes opaque to its own radiation. Photons can't escape easily. They scatter repeatedly off electrons and atoms. The core becomes trapped by its own light. Second, the trapped radiation pressure briefly halts further collapse. The core reaches a quasi-stable state, lasting perhaps a few thousand years. Matter continues falling onto this stable core from the surrounding gas. The envelope grows more massive while the core stays relatively constant. Scientists call this configuration a quasi-star. It's not quite a star because fusion doesn't dominate the energy generation. It's not yet a black hole because an event horizon hasn't formed. It's an intermediate state unique to direct collapse. Third, as the envelope mass increases, the core gets squeezed harder. Compression raises the core temperature. Normal matter cooling mechanisms can't remove heat fast enough. The core temperature climbs to 1 billion degrees. At these temperatures, a new cooling mechanism activates: neutrino emission. Neutrinos are ghostly particles that barely interact with matter. They can escape from regions so dense that even light gets trapped. When matter reaches temperatures above 1 billion degrees, it produces neutrinos through various quantum processes. Those neutrinos carry away enormous amounts of energy. They provide a cooling mechanism that works even in the densest regions of collapsing gas clouds. Fourth, neutrino cooling triggers catastrophic collapse. The core loses pressure support as neutrinos carry away heat. Temperature drops even as density increases. This violates the normal relationship between temperature and density. Under normal circumstances, compressing gas heats it, but with neutrino cooling, compressing gas can cool it. This thermal instability causes runaway collapse. Fifth, the core collapses inward at nearly the speed of light. Within hours or days, it shrinks from the size of our solar system to the size of a city to the size of a basketball. Space itself warps under the extreme gravity. Time dilation becomes severe. An outside observer sees the collapse slow down and freeze as the matter approaches the event horizon. But from the perspective of the infalling matter, the collapse proceeds at breakneck speed. Finally, the event horizon forms. A boundary in space-time appears, marking the point of no return. Anything crossing this boundary can never escape. The black hole is born. Its initial mass might be around 10 to 20 solar masses, just the core material that collapsed first. But it sits in the middle of a massive envelope, still falling inward. That envelope provides enormous amounts of matter for rapid accretion. The newborn black hole begins feeding immediately. The surrounding gas doesn't magically disappear when the black hole forms. It continues falling inward now into the black hole rather than onto a quasi-star core. The accretion rate is tremendous, far exceeding the Eddington limit. The black hole gains mass rapidly, doubling in weight every few months initially. This super Eddington growth phase lasts until the radiation from the accretion disk becomes powerful enough to blow away the remaining gas envelope. At that point, the black hole emerges from its cocoon, revealed as a bright X-ray and radio source embedded in ionized gas. This is the state the infinity galaxy black hole occupies now. It's actively feeding, still growing, but no longer buried in an optically thick envelope. The team calculated that the formation event occurred relatively recently in the galaxy collision timeline. The black hole is young, still growing, still changing. This makes it an incredibly valuable object for studying direct collapse. It hasn't had time to grow enormously or merge with other black holes. It represents something close to a pristine heavy seed. Everything hinged on measuring one number. How fast is the black hole moving compared to the gas surrounding it? This single measurement would determine whether the direct collapse theory was correct or whether simpler explanations could account for the observations. The team knew that velocity measurement would make or break their case. If the black hole was racing through the collision zone at high velocity, it probably got ejected from one of the galaxy cores. Black holes can be ejected during violent mergers through a process called gravitational recoil. When two black holes spiral together and merge, the gravitational waves they emit can carry momentum. If those waves emit asymmetrically, they can kick the merged black hole like a rocket. Some ejected black holes travel at thousands of miles per second, fast enough to escape their host galaxy entirely. An ejected black hole would have a velocity significantly different from the surrounding gas. The gas in the collision zone moves at the orbital velocity of the colliding galaxies, roughly 300 miles per second. An ejected black hole might move at 1,000 miles per second or more. The velocity difference would be obvious and conclusive. If the black hole sat motionless relative to the gas, that would support direct collapse. A black hole born from the gas should share the gas's velocity. They formed from the same material. They should move together through space. A velocity match would indicate the black hole is embedded in the gas cloud rather than passing through it. The team applied for additional observation time on the James Webb Space Telescope. They needed high-resolution spectroscopy to measure velocities precisely. Webb's instruments can split light into detailed spectra, revealing the wavelengths of emission lines with extreme accuracy. Those wavelengths encode velocity information through the Doppler effect. The observations came through. The team analyzed the data with mounting excitement. They measured the velocity of ionized gas throughout the collision zone. Gas near one galaxy core moves toward us at 270 miles per second. Gas near the other core moves away at 290 miles per second. The collision zone shows a complex velocity field with gas moving at different speeds in different locations. Then they measured the black hole's velocity. They used emission lines from the hot gas in the immediate vicinity of the black hole, gas so close to the event horizon that it must be moving with the black hole. Those emission lines revealed a velocity of 280 miles per second, right in the middle of the gas velocity distribution, not moving fast relative to the surrounding gas, not ejected, not passing through, embedded. The velocity match was even better than required. The team had proposed that if the velocities agreed within 30 miles per second, that would be strong evidence for direct collapse. The actual measurement showed agreement within 10 miles per second. The black hole moves with the gas. It's part of the gas cloud. It formed there. This result eliminated the ejection scenario. An ejected black hole would show obvious velocity differences. The measurement showed no such difference. The black hole isn't a runaway from either galaxy core. The velocity test also eliminated the chance superposition scenario. If a third background galaxy existed, and its central black hole appeared to lie in the collision zone only due to projection effects, that background black hole would show very different velocity. Background galaxies recede from us due to cosmic expansion. Their velocities depend on their distances. A background galaxy would show a substantially redshifted velocity, completely inconsistent with the collision zone gas. The measurements confirm the black hole sits physically in the collision zone. It's not projected from behind. It's not racing through at high speed. It's embedded in the gas bridge between the two galaxies. And it moves with that gas as if it were born from that gas. Van Dockum called this result the key finding they were after. The velocity match strongly supports direct collapse formation. Combined with the black hole's location, its mass, the ionized gas distribution, and the extreme turbulence in the collision zone, the evidence points toward one conclusion: this black hole formed through direct collapse of the collision zone gas. The team couldn't say definitively they'd found direct collapse. Science rarely deals in certainties, but they could say the evidence strengthened the case substantially while eliminating alternative explanations. This might be humanity's first glimpse of direct collapse caught in action, the birth of a heavy seed black hole in the modern universe. But the story doesn't end here. There's more to the infinity galaxy than one unusual black hole. The discovery gets stranger. Scientists love rules because rules reveal patterns in nature. The 30 miles per second rule became the threshold that separated one formation scenario from another. If the black hole's velocity differed from the gas by more than 30 miles per second, direct collapse became unlikely. If the velocity matched within 30 miles per second, direct collapse became the leading explanation. This simple rule distilled complex physics into one testable prediction. Why 30 miles per second specifically? The number comes from understanding how gas clouds move and how black holes interact with those clouds. Gas in the collision zone doesn't move uniformly. Different regions have different velocities. Turbulence creates velocity variations of about 20 to 30 miles per second across the zone. That's the natural scatter in the gas motion. A black hole born from that gas should share the gas's average velocity. It might differ slightly due to local velocity variations at its formation site, but that difference should fall within the turbulence scatter. 30 miles per second represents a conservative upper limit. Anything within that range suggests the black hole and gas are dynamically coupled. An ejected black hole tells a different story. Gravitational recoil, kicks from black hole mergers, can reach 1,000 miles per second or higher. Even a relatively gentle ejection produces velocities of several hundred miles per second. The difference would be unmistakable. You don't need precise measurements to tell the difference between 30 miles per second and 300 miles per second. The same logic applies to runaway black holes. Sometimes supermassive black holes get ejected from galaxy cores through three-body interactions. When three massive objects orbit each other, the system becomes chaotic. Eventually, one object gets flung out at high velocity, while the other two bind more tightly. If the infinity galaxy black hole were a runaway ejected through this mechanism, it would show high velocity. Interloper scenarios also fail the velocity test. Imagine a third galaxy that happens to align with the collision zone from our viewing angle. Its central black hole would appear to sit between the two main galaxies, even though it's much farther away. But that third galaxy would have its own velocity determined by cosmic expansion and its motion through space. That velocity would almost certainly differ dramatically from the collision zone gas. The velocity measurement cut through these alternative explanations with surgical precision. One number eliminated multiple scenarios. The team knew this when they designed their observation proposal. They focused their entire follow-up strategy on obtaining the highest quality velocity measurements possible. Webb spectrograph delivered. The instrument can measure velocities to an accuracy of about 3 miles per second under ideal conditions. The infinity galaxy observations achieved nearly that precision. The uncertainty in the velocity measurement was only about 5 miles per second, more than good enough to test the 30 miles per second rule. The result exceeded expectations. The black hole velocity matched the gas velocity to within 10 miles per second, well within the 30 miles per second threshold. The match was so close that it essentially proved the black hole and gas moved together as a single system. Think about what this means. The black hole isn't visiting this region. It's not passing through. It's not projected from a background galaxy. It lives in the collision zone. It formed there, or it's been there so long that it perfectly coupled to the gas motion. Given the young age of the collision and the active feeding signatures, the formation in place explanation makes far more sense. The 30 miles per second rule worked. It predicted that a direct collapsed black hole should match gas velocities within this threshold. The measurement confirmed the prediction. One more piece of evidence supporting an extraordinary claim. But the team wasn't done finding surprises. The Infinity Galaxy held secrets nobody anticipated. The Infinity Galaxy doesn't host one supermassive black hole. It hosts three. Each of the two colliding galaxy cores retained its original central black hole. Both are actively feeding. Both emit X-rays and radio waves. Both weigh millions of times the sun's mass. And then there's the third black hole floating between them in the collision zone. Three supermassive black holes in one system. This discovery emerged gradually as the team analyzed data from multiple telescopes. The Chandra X-ray Observatory detected three distinct X-ray sources, one in each galaxy core and one in the middle. X-ray emission from supermassive black holes has a characteristic signature. The energy spectrum and variability patterns are distinctive. All three sources showed the telltale signs. The Very Large Array confirmed the picture with radio observations. Three bright radio sources appeared in the same locations as the X-ray sources. Black holes launch jets of particles at nearly light speed when they feed actively. Those jets emit radio waves through a process called synchrotron radiation. The radio detections proved all three black holes are actively accreting matter. The Webb infrared data showed broad emission lines from all three locations. Broad lines indicate gas moving at extremely high velocities, thousands of miles per second. Only supermassive black holes generate velocity fields that extreme. The spectroscopic signatures confirmed three active galactic nuclei in one system. This triple system is extraordinarily rare. Finding even two active supermassive black holes in one system is uncommon. They exist when galaxies collide, and both central black holes remain active during the merger. But those are binary systems. Triple systems require something more unusual. The standard formation scenario for triple black hole systems involves three different masses and different feeding rates. The two galaxy core black holes weigh roughly 10 million solar masses, each based on their X-ray luminosities and the orbital velocities of surrounding stars. They're mature, supermassive black holes that grew over billions of years within their host galaxies. The collision zone black hole weighs about 1 million solar masses, 10 times less massive than its companions. It's the baby of the family, the youngest member, still growing rapidly, while the older black holes feed at more sedate rates. The system's future evolution is fascinating to consider. The two galaxy cores will eventually merge completely. Their central black holes will spiral together over tens of millions of years. They'll emit gravitational waves as they orbit. Eventually, they'll merge in a catastrophic collision that will send ripples through space-time, detectable by gravitational wave observatories. But what happens to the third black hole? It might merge with one of the others. It might get ejected from the system through three-body interactions. It might survive and orbit in the final merged galaxy. Computer simulations suggest all three outcomes are possible, depending on the exact trajectories and timing. The triple system makes the Infinity Galaxy a laboratory for studying black hole dynamics. Most systems contain only one black hole. Binary systems are rare enough. Triple systems are exceptional. Having one member be a potential direct collapse black hole makes this system one of a kind. The discovery also raised questions. If one direct collapse black hole formed in this collision zone, could others form elsewhere? Could galaxy collisions routinely produce heavy seeds? The team started wondering if direct collapse might be more common than anyone suspected, not limited to the early universe, not requiring pristine primordial gas, just requiring violent enough collisions to create the right conditions. The implications kept expanding. But first, they needed to understand exactly how the three telescopes work together to uncover this system. Black holes are invisible by definition. Light can't escape from inside the event horizon. So how do we detect them? We look for the mess they make while eating. And that mess shines brightly in X-rays and radio waves. The Chandra X-ray Observatory and Very Large Array provided crucial evidence that three black holes are actively feeding in the infinity galaxy. X-rays reveal the hottest material in the universe. Gas falling into a black hole accelerates to nearly light speed. Friction in the accretion disk heats this gas to tens of millions of degrees. At those temperatures, atoms move so fast, they collide with tremendous energy. Those collisions produce X-rays. The hotter the gas, the higher the X-ray energy. Chandra detected hard X-rays from all three locations. Hard X-rays are high-energy photons that can only be produced by extremely hot gas or by high-energy particle interactions. The X-ray spectra showed characteristic features of black hole accretion, power law distributions, ion emission lines, variability on timescales of hours to days. The collision zone black hole produces about 1/10 the X-ray luminosity of the two core black holes. This matches expectations for a smaller, younger black hole. Less mass means a shallower gravitational well. Less gravitational energy gets converted to radiation during accretion. The X-ray measurements provided an independent check on the mass estimates from other methods. Chandra also detected extended X-ray emission surrounding the collision zone black hole. This diffuse emission comes from hot ionized gas heated by shocks and radiation from the black hole. The extent of this hot gas matches the green glowing region visible in Webb images. Multiple wavelengths paint a consistent picture of a black hole embedded in a vast cloud of ionized gas. Radio observations tell a different but complementary story. The Very Large Array detected synchrotron radiation from all three black hole locations. Synchrotron emission occurs when electrons spiral around magnetic field lines at nearly light speed. The spiraling electrons emit radio waves. The wavelength and intensity of the emission encode information about the magnetic field strength and electron energies. Black holes generate powerful magnetic fields in their accretion disks. These fields channel particles into jets that shoot outward at 90% light speed or faster. The jets extend far beyond the accretion disk, sometimes reaching hundreds of thousands of light years into intergalactic space. They're the most energetic, continuous outflows in the universe. The Infinity Galaxy Collision Zone black hole shows radio jets extending about 5,000 light-years in opposite directions. The jets plow into surrounding gas, creating shock waves visible in radio wavelengths. These radio lobes prove the black hole is actively launching jets right now. It's not dormant, it's feeding vigorously. The radio jets also provide velocity information. The approaching jet appears brighter than the receding jet due to relativistic beaming. Light from material moving toward us gets compressed and brightened. Light from material moving away gets stretched and dimmed. The brightness ratio between approaching and receding jets reveals the jet velocity. The collision zone black hole launches jets at roughly 70% light speed. Combined observations from Webb, Chandra, and the Very Large Array created a complete portrait. Webb sees the ionized gas in infrared light. Chandra sees the superhot accretion disk in X-rays. The Very Large Array sees the jets in radio waves. Each telescope contributes unique information. Together, they confirm an actively accreting supermassive black hole. This multi-wavelength approach is essential for modern astronomy. No single telescope can capture the full story. Black holes emit across the electromagnetic spectrum, from radio waves to gamma rays. Each wavelength reveals different physics. Radio shows jets and magnetic fields. Infrared shows dust and ionized gas. X-rays show the hottest material closest to the event horizon. The Infinity Galaxy observations demonstrate the power of combining data from multiple observatories. Webb provided the initial discovery and detailed infrared imaging. Chandra confirmed active black holes through X-ray detection. The Very Large Array revealed jet structures through radio mapping. Each observation strengthened the case for 3 active supermassive black holes. But none of this would have happened without one crucial starting point: a team of astronomers hunting through archival data for cosmic oddities. The Infinity Galaxy was hiding in plain sight, buried in hundreds of terabytes of telescope data, waiting for someone to notice. Peter Van Dokkum and Gabriel Brammer weren't looking for black holes specifically. They were hunting for anything weird, anything that didn't fit patterns, anything that made them stop scrolling and say, "What is that?" The data came from Cosmos Webb, one of the largest surveys conducted by the James Webb Space Telescope. The survey observed a region of sky in the constellation Sextans, capturing deep images of more than 1 million galaxies across cosmic history. The observations took 255 hours of telescope time, generating massive datasets. James Webb collects far more data than any human team can analyze in real time. The telescope observes constantly. Data flows down to Earth continuously. That data gets archived in public databases where any astronomer can access it. But accessing is one thing. Actually looking through millions of images is another. The archive contains treasures, but they're hidden in an ocean of data. Van Dokkum and Brammer developed algorithms to search for unusual objects. They wrote code to identify galaxies with weird shapes, strange colors, or unexpected brightness patterns. The algorithms flagged thousands of candidates. Then came the tedious part: visually inspecting each candidate to separate truly interesting objects from false alarms. They found the Infinity Galaxy during one of these inspection sessions. The figure 8 shape jumped out immediately. Galaxy mergers are common, but perfect symmetrical rings forming an infinity symbol? That's rare. Van Dokkum sent the image to colleagues. Everyone agreed this deserved closer examination. The initial Webb image showed the 2 bright cores and ring structures. But the really interesting feature was that green bridge stretching between them. The hydrogen emission looked intense and extended. Something was lighting up that gas. The team checked archival data from other surveys. The Infinity Galaxy had been observed before by Hubble and ground-based telescopes, but those observations didn't reveal the details visible to Webb. Webb's infrared vision cuts through dust that blocks visible light. The collision zone contains enormous amounts of dust from destroyed stars and gas clouds. Visible light observations show only the brightest regions. Infrared penetrates the dust, revealing the full structure. Webb saw what previous telescopes missed. The discovery process exemplifies modern astronomy. Telescopes generate data faster than humans can analyze it. The James Webb Space Telescope alone produces about 60 gigabytes of data per day. The Hubble Space Telescope archive contains over 175 terabytes. The upcoming Vera Rubin Observatory will generate 20 terabytes per night. We're drowning in cosmic data. This creates opportunities for discovery. Archival searches frequently uncover objects that previous observers missed. The original telescope operators might have been looking for something specific. They analyzed their targets and moved on. Years later, someone searching for something completely different notices an interesting background object. The same data gets reanalyzed for new purposes. The Infinity Galaxy existed in Webb's data for months before Van Dokkum and Brammer noticed it. Other astronomers likely saw it while scrolling through Cosmos Webb images, but didn't recognize its significance. It takes experience and intuition to spot the unusual among the mundane. It takes knowing what questions to ask. Van Dokkum immediately suspected something important lurked in that collision zone. The symmetry was too perfect. The emission too bright. He contacted colleagues who had access to Chandra and the Very Large Array. They requested follow-up observations targeting the Infinity Galaxy specifically. Those observations detected the 3 X-ray sources and radio emissions. The discovery snowballed from there. Each new observation revealed additional details: the velocity measurements, the ionization mapping, the jet structures. What started as a weird-looking galaxy in an archived image became one of the most important black hole discoveries in recent years. This is how most major discoveries happen in modern astronomy. Not through targeted searches, though those are important, but through serendipity, through someone noticing something odd and deciding to investigate, through algorithms flagging unusual candidates and humans recognizing significance. The Infinity Galaxy discovery reminds us that the universe still holds surprises. We've mapped billions of galaxies, we've measured cosmic expansion, we've detected gravitational waves, but we're still finding phenomena that challenge our theories, still uncovering objects that shouldn't exist according to our models, still learning that nature is more creative than our imaginations, and the Infinity Galaxy had more secrets to reveal. The green glow between the galaxy cores isn't uniform. It's not a smooth bridge of gas. Close examination reveals structure, filaments, knots, regions of varying brightness. This structure tells a story about what's happening in the collision zone. Every detail in the ionization pattern provides clues about the black hole hiding within. Ionized hydrogen emits light through a specific quantum mechanical process. A free electron drifts through space. It encounters a hydrogen ion, which is just a proton without its electron. The electron gets captured by the proton, forming a neutral hydrogen atom again. But the electron doesn't drop directly to the lowest energy level. It cascades down through higher levels first, and each transition releases a photon at a specific wavelength. One of these transitions produces light at 1.65 microns in the infrared spectrum. This is the emission line. Webb's instruments detect and display as green in false color images. The brightness of this emission directly indicates how much hydrogen is being ionized. Brighter regions mean more ionization. More ionization means more radiation from the black hole. The brightest ionization sits directly on top of the black hole's position. The emission drops off with distance from the black hole, following a predictable pattern. Close to the black hole, nearly all hydrogen is ionized. Farther away, only a fraction is ionized. At large distances, the gas returns to neutral atomic hydrogen. This gradient maps the radiation field from the black hole. Scientists can measure the total luminosity needed to produce the observed ionization. The calculation involves counting ionized atoms and knowing how long they stay ionized before recombining. Multiply the ionization rate by the volume of ionized gas, and you get the total number of ionizing photons required per second. That number reveals how much radiation the black hole emits. The collision zone black hole needs to produce about 10 to the power of 45 ionizing photons every second to explain the observed emission. That's an incomprehensibly large number. For comparison, our Sun produces about 10 to the power of 45 photons per second total across all wavelengths. This black hole produces that many ionizing photons alone, each one energetic enough to rip electrons off atoms. That radiation comes from the accretion disk. As matter spirals into the black hole, gravitational energy converts to heat and radiation. The efficiency of this conversion determines the luminosity. Black holes convert about 10% of infalling mass to energy. That's far more efficient than nuclear fusion in stars, which converts less than 1% of mass to energy. The extended ionization proves the black hole has been actively feeding for at least a few million years. Ionization doesn't propagate instantaneously. Radiation travels at light speed, so ionizing a region 10,000 light-years across takes 10,000 years minimum. The observed ionization pattern requires continuous emission over millions of years. This black hole isn't experiencing a brief feeding episode. It's been eating steadily. The ionization signature also reveals turbulence in the gas. The spectral lines show broadening consistent with velocity dispersions of several hundred miles per second. Different parts of the ionized cloud move at different velocities. This confirms the extreme turbulence inferred from other observations. The gas isn't calm and quiescent, it's violently chaotic. Webb detected multiple ionization states of different elements in the collision zone. Not just ionized hydrogen, but also ionized helium, oxygen, and neon. Each element requires different energy to ionize. Hydrogen ionizes easily. Helium requires more energetic photons. Oxygen and neon require even higher energies. Finding these elements in multiple ionization states indicates a hard radiation spectrum typical of black hole accretion. The team mapped the ionization across the entire collision zone. They created detailed images showing how ionization varies with position. The results confirmed that ionization is strongest near the black hole and decreases with distance. No other radiation source exists in the collision zone capable of producing this pattern. The ionization signature uniquely points to a supermassive black hole. This ionization mapping provided another key piece of evidence. The glowing gas isn't just near the black hole, it surrounds the black hole in all directions. The black hole sits embedded within an extended ionized cloud. This geometry is exactly what direct collapse predicts. A heavy seed black hole born from a gas cloud should remain embedded in that cloud, ionizing and accreting it simultaneously. The ionization signature converted the abstract concept of direct collapse into concrete, observable predictions that matched the data. Theory and observation aligned. Science progresses by eliminating wrong answers as much as finding right ones. The Infinity Galaxy team spent as much time ruling out alternative explanations as they did supporting direct collapse. Every competing theory needed careful consideration and refutation. The process was methodical and thorough. Alternative explanation 1. The black hole was ejected from one of the galaxy cores during the collision. This scenario isn't implausible. Galaxy mergers can eject black holes through gravitational slingshot effects. When two massive objects interact, they can throw each other around violently. Perhaps one galaxy's central black hole got launched toward the collision zone. The velocity test killed this explanation. An ejected black hole would race through space at hundreds or thousands of miles per second relative to the surrounding gas. The measurements showed the black hole moving with the gas, not through it. Velocity difference less than 10 miles per second. That's not an ejection scenario. That's an embedded object. Alternative explanation 2. A third background galaxy sits behind the collision zone, perfectly aligned from our viewing angle. Its central black hole appears to float between the two main galaxies due to projection effects. Astronomers call these chance superpositions, and they do occur. Multiple lines of evidence eliminated this possibility. First, the velocity test again. A background galaxy would have a completely different redshift, reflecting its greater distance. The measurements showed the black hole has the same redshift as the collision zone gas. It sits at the same distance from Earth. It's physically in the collision zone, not behind it. Second, the ionization pattern. A background black hole wouldn't ionize the collision zone gas. The ionization would surround the background galaxy instead. The observed emission clearly associates with the collision zone gas, not with any background galaxy. Third, careful examination of Webb's deep images revealed no third galaxy at that location. The team looked for stellar populations, galaxy structure, anything indicating a background galaxy. They found nothing. If a galaxy existed there, Webb would see it. Alternative explanation 3. The collision zone gas contains numerous smaller black holes rather than one supermassive black hole. Perhaps dozens of stellar mass black holes formed from massive stars and now orbit within the gas cloud. Their combined emission might mimic a single supermassive black hole. The spectroscopic data rejected this scenario. Multiple small black holes would produce broadened but multi-peaked emission lines as different objects move at different velocities. The observed emission lines show single, smooth profiles, consistent with one object. The X-ray and radio emission are also point-like, coming from a single compact source, rather than distributed across multiple locations. Alternative explanation 4. The collision triggered an intense starburst in the collision zone. Maybe hundreds of massive stars formed and quickly evolved into black holes. Those stellar mass black holes might have merged into an intermediate mass black hole, weighing thousands of solar masses. The timeline doesn't work. The collision happened billions of years ago, but stellar evolution and black hole mergers take time. Building a million solar mass black hole from stellar mergers requires at least hundreds of millions of years. More importantly, the collision zone shows no evidence of past star formation, no supernova remnants, no stellar populations of the right age. The turbulence prevented star formation, which is the whole point of direct collapse. Alternative explanation 5. The black hole formed through normal stellar evolution somewhere else, then migrated into the collision zone through dynamical interactions. Black holes can wander through galaxies. Maybe this one wandered into exactly the right spot. The probability argument defeats this scenario. Supermassive black holes weighing millions of solar masses don't wander. They're too massive. They sit at galaxy centers held by gravity. Getting one to migrate to an off-center location requires extraordinary circumstances, and having it arrive precisely in the collision zone with precisely the right velocity to match the gas, the coincidence is too extreme. Each alternative explanation failed for specific, testable reasons. The observations systematically eliminated every competing theory. What remained was direct collapse. Not proven absolutely, because science doesn't deal in absolute proof, but supported by multiple independent lines of evidence, while alternatives fell to observation and logic. The team didn't stop there. They considered even more exotic possibilities. Maybe the black hole was primordial, formed during the Big Bang itself. But primordial black holes that massive have never been detected and probably don't exist. Maybe it's actually a wormhole or naked singularity instead of a black hole. But those hypothetical objects behave identically to black holes for observational purposes. So the distinction doesn't matter for this analysis. Every alternative examined, every alternative rejected. The evidence pointed one direction: direct collapse. The early universe was a different place. Conditions existed then that disappeared as the cosmos aged. Direct collapse theory. The window closed. The infinity galaxy sits at redshift 0.33. In cosmic time, that means we're observing it as it was about 3.6 billion years ago. That's roughly 10 billion years after the supposed direct collapse window closed. The universe was already old and metal enriched by then. Traditional theory says direct collapse shouldn't be possible at such late times. This timing puzzle troubled the team initially. How could they claim direct collapse if the infinity galaxy formed billions of years too late? The answer lies in understanding that the early universe scenario and the galaxy collision scenario involve different physics. They both produce direct collapse, but through different mechanisms. Early universe direct collapse relies on Lyman-Werner radiation preventing molecular hydrogen formation. This requires pristine gas with no metal contamination. The window for these conditions existed only briefly in cosmic history. After the universe became metal-enriched, this pathway closed. Galaxy collision direct collapse relies on turbulence and pressure preventing star formation. This doesn't require pristine gas. It works even in metal-enriched environments. The extreme conditions of a violent head-on collision override normal star formation physics through purely mechanical means. Turbulence tears apart molecular clouds before they can form stars. Shockwaves compress gas faster than cooling can dissipate the heat. This means direct collapse can occur at any cosmic epoch if the collision conditions are right. It's not limited to the early universe. The mechanism differs, but the result is the same. A heavy seed black hole forms from direct gas collapse. The infinity galaxy proves this can happen in the modern universe. This realization expands the significance of the discovery. Direct collapse isn't a relic process from the early universe. It's an ongoing phenomenon. Galaxy collisions occur throughout cosmic history. Many collisions might create the conditions for direct collapse. Heavy seeds might be forming constantly, scattered throughout the universe, wherever violent enough collisions occur. The team started calculating how often appropriate collisions happen. Major galaxy mergers occur roughly once per billion cubic light-years per billion years. Only a fraction of those are head-on collisions with the right geometry and gas content. Maybe 1 in 100 mergers creates direct collapse conditions. That suggests direct collapse events occur perhaps once per 100 billion cubic light-years per billion years. Sounds rare, but the observable universe contains about 400 billion cubic light-years. Over cosmic history, direct collapse through galaxy collisions might have produced thousands of heavy seed black holes. Not enough to account for all supermassive black holes, but a significant population. Many of these collision-triggered direct collapse events might have occurred at high redshift in the early universe. Galaxy collision rates were higher then because galaxies were closer together. Combining early universe collisions with the traditional Lyman-Werner radiation pathway suggests direct collapse might be more common than anyone thought. The redshift window isn't a narrow period in the early universe. It's any time and place where the right conditions occur. That window remains open today. The Infinity Galaxy proves it. Direct collapse is happening right now somewhere in the cosmos. We just have to find these events. This changes the search strategy. Instead of only looking at the earliest, most distant galaxies, astronomers should examine recent galaxy mergers. Look for collisions that produced intense turbulence. Search for black holes in unusual locations. The next direct collapse discovery might be relatively nearby in cosmic terms. Traditional direct collapse theory demands gas purity that borders on the obsessive. 1 part in 100,000 metal contamination ruins everything. The gas must be essentially identical to the primordial composition emerging from the Big Bang. 75% hydrogen, 25% helium, and almost nothing else. No carbon, no oxygen, no nitrogen, no elements heavier than helium. This purity requirement stems from how efficiently heavy elements cool gas. Carbon and oxygen are particularly devastating. These elements have electronic transitions that radiate infrared light very efficiently. Even trace amounts of carbon or oxygen allow gas to cool rapidly by emitting infrared photons. Cool gas fragments into stars. Direct collapse fails. The early universe started pristine by definition. The Big Bang produced only hydrogen, helium, and tiny amounts of lithium. No heavier elements existed until the first stars formed and died. Gas clouds in the first few 100 million years of cosmic history were naturally metal-free. They met the purity requirement automatically. But stars change everything. Massive stars forge heavy elements through nuclear fusion. Carbon and oxygen form in stellar cores. When those stars explode as supernovas, they scatter these elements across space. Each generation of stars increases cosmic metallicity. The universe becomes progressively polluted with metals. Pristine gas becomes increasingly rare. The Infinity Galaxy collision zone gas isn't pristine. Spectroscopic measurements reveal metal abundances around 10 to 30% of solar metallicity. That's vastly above the traditional direct collapse threshold. This gas contains thousands of times too much carbon and oxygen. By conventional theory, it should have cooled rapidly and formed stars. Direct collapse should be impossible. Yet a million solar mass black hole sits embedded in this metal-enriched gas. Something allowed direct collapse despite the metal contamination. The answer is turbulence and compression. These mechanical processes can override chemical cooling. When gas is compressed rapidly through shock waves, heating occurs faster than radiative cooling can remove it. Even efficient metal line cooling can't keep up with violent compression. The gas stays hot because energy gets pumped in faster than it can radiate away. Think of trying to cool a pot of water by turning on a fan while someone continuously adds heat. Eventually, the heating wins. Turbulence prevents fragmentation through a different mechanism. Even if local regions of gas cool slightly, turbulent flows tear them apart before they can collapse. The gas never stays coherent long enough to form stars. Fragmentation requires thousands to millions of years of relatively calm collapse. Turbulence disrupts that process. The collision also compressed gas so rapidly that star formation didn't have time to proceed through its normal stages. From the initial shockwave to black hole formation probably took less than 10 million years. Star formation takes tens to hundreds of millions of years to convert a significant fraction of gas into stars. The black hole formed before star formation could consume the gas reservoir. This discovery fundamentally changes direct collapse theory. Pristine gas isn't required if other mechanisms prevent star formation and cooling. Turbulent, rapidly compressed, metal-enriched gas can undergo direct collapse. The chemistry matters less than the dynamics. This opens new possibilities. Many environments in the universe feature intense turbulence and rapid compression. Galaxy collisions obviously qualify, but also galaxy cluster mergers, where multiple galaxies crash together simultaneously, and tidal disruption events, where gas streams get torn from galaxies, and the cores of massive starbursting galaxies, where supernova-driven winds create turbulence. Each of these environments might occasionally produce conditions suitable for direct collapse. The parameter space expands dramatically when you remove the pristine gas requirement. Direct collapse transforms from a rare early universe phenomenon into a potentially common process operating throughout cosmic history. The team published these findings with careful caveats. They couldn't prove definitively that the infinity galaxy black hole formed through direct collapse, but they demonstrated that metal-enriched gas can satisfy direct collapse conditions if turbulence is sufficiently extreme. This theoretical framework predicts observable signatures that match the infinity galaxy data. The pristine gas requirement was always the most challenging aspect of early universe direct collapse theory. Finding metal-free gas clouds bathed in Lyman-Werner radiation but shielded from supernova ejecta seemed almost impossible. The revised theory, requiring only extreme turbulence, is far less restrictive. Nature can achieve extreme turbulence through galaxy collisions much more easily than it can maintain pristine gas clouds in the evolving universe. The infinity galaxy represents something unprecedented, a test case for direct collapse in the modern universe, a laboratory for studying processes that scientists thought only occurred during cosmic dawn. The collision created conditions that shouldn't exist billions of years after the Big Bang. It's an exception that proves the rule, while simultaneously rewriting the rule. Modern galaxies live in a metal-enriched cosmos. Billions of generations of stars have lived and died. Supernovas have scattered heavy elements throughout intergalactic space. The average metallicity of gas between galaxies now reaches 10 to 30% of solar values. Inside galaxies, metallicity exceeds solar values. Finding metal-free gas anywhere in the modern universe seems impossible. Modern galaxies also exist in relatively evolved states. Most have already experienced multiple mergers. Their structures reflect billions of years of evolution. They've converted most of their gas into stars. Massive gas reservoirs like those in the early universe are rare. The fuel for forming anything massive is depleted. Modern black holes already exist at galaxy centers. Almost every major galaxy hosts a supermassive black hole that formed billions of years ago. Those black holes grew through accretion and mergers over cosmic time. They've reached equilibrium sizes related to their host galaxy masses. The era of rapid black hole formation is long past. Given these conditions, direct collapse shouldn't happen in the modern universe. All the prerequisites are absent. Metal contamination poisons the gas. Massive gas reservoirs are depleted. Black holes already exist where they're going to exist. The window closed long ago. The Infinity Galaxy violates these expectations. The head-on collision between two gas-rich spiral galaxies recreated early universe conditions through purely mechanical means. The collision compressed billions of solar masses of gas into a small volume. Turbulence from the shockwaves prevented star formation despite metal enrichment. The timescale of the collision was shorter than the star formation timescale. This makes the Infinity Galaxy a modern exception, an event that shouldn't produce direct collapse, but apparently did. The discovery forces scientists to reconsider which processes can trigger heavy seed formation. It's not just about gas chemistry and radiation fields. It's also about dynamics, timescales, and violent events. Other modern exceptions might exist. The team began searching archival data for similar collisions. They looked for galaxy mergers with bright ionized gas bridges between cores. They searched for X-ray sources in unusual locations. They examined velocity fields in merging systems. If the Infinity Galaxy can produce direct collapse, other collisions might too. Several candidate systems emerged. One shows a bridge of ionized gas between merging galaxies with a suspicious X-ray source in the middle. Another displays extreme turbulence in its collision zone. A third features asymmetric ring structures, suggesting a high-energy impact. None are as clear-cut as the Infinity Galaxy, but they deserve follow-up observations. If direct collapse occurs in multiple modern collisions, it suggests the process is more common than traditional theory predicted. Every major head-on collision between gas-rich galaxies might have a chance of producing a heavy seed. The probability might be low, perhaps 10% or less, but non-zero. Extrapolating across cosmic history, this mechanism might have produced thousands of heavy seed black holes. Most would have formed during earlier epochs, when galaxy collision rates were higher and gas fractions were larger, but some continue forming even today. The modern exceptions also help explain an observational puzzle. Astronomers find more intermediate mass black holes than theories predict. Black holes weighing 10,000 to 1 million solar masses exist in surprising numbers. Traditional theory struggles to explain them. They're too massive to come from stellar evolution, too small to be ancient galaxy core black holes. They don't fit neatly into either category. Direct collapse in galaxy collisions might create these intermediate mass black holes. A heavy seed forms weighing 1 million solar masses. It never grows much larger because the gas supply depletes. It remains stranded at intermediate mass. These objects would be scattered throughout large galaxies and galaxy clusters, wherever violent collisions occurred in the past. The Infinity Galaxy might not be exceptional after all. It might be representative of an entire population of collision-triggered direct collapse events. We just haven't recognized them yet, because we weren't looking in the right places with the right tools. Quasars are the brightest sustained beacons in the universe. They outshine entire galaxies. Some emit more light than 1 trillion suns combined, and they're compact, concentrated into regions smaller than our solar system. These objects bewildered astronomers when first discovered in the 1960s. Only later did scientists realize quasars are supermassive black holes feeding voraciously. The light comes from the accretion disk. As matter spirals into the black hole at nearly light speed, friction converts gravitational energy to radiation. The process is extremely efficient. About 10% of the infalling mass gets converted to energy. Compare that to nuclear fusion, which converts less than 1%. Black hole accretion is the most efficient sustained energy generation process in nature. To power a bright quasar requires a supermassive black hole weighing at least 100 million solar masses. Bigger black holes produce brighter quasars. The most luminous quasars host black holes weighing billions of times the sun's mass. These cosmic monsters dominate the energy output of their host galaxies. Quasars were common in the early universe. The James Webb Space Telescope finds them at redshift 6, 7, even approaching redshift 10. These ancient quasars existed when the universe was less than 1 billion years old. Some blazed to life just 500 million years after the Big Bang. This creates the supermassive black hole formation paradox that direct collapse theory attempts to solve. To power a quasar with a billion solar mass black hole at redshift 7 requires that black hole to form and grow extremely quickly. Starting from a 10 solar mass stellar remnant and growing at the Eddington limit produces a black hole far too small. The timeline doesn't work. But starting from a million solar mass, heavy seed changes everything. That 1,000-fold head start compresses the required growth time from impossible to barely feasible. A heavy seed forming at redshift 20 has enough time to grow to billions of solar masses by redshift 7 if it feeds continuously at the Eddington limit. The infinity galaxy discovery strengthens the connection between direct collapse and early quasars. If heavy seeds can form through galaxy collisions in the modern universe, they certainly could form during the early universe when conditions were even more favorable. Collision rates were higher, gas fractions were larger, turbulence was more common. Every early galaxy merger might have risked producing a heavy seed. This solves the quasar population problem. Theoretical calculations predicted too few massive black holes in the early universe to explain the observed quasar numbers. Adding a population of heavy seeds from direct collapse increases the number of black hole formation sites. More seeds mean more potential quasars. The observational signatures match. Early quasars show intense ionized gas emission surrounding their cores. The gas is turbulent and metal-enriched. X-ray and radio emission indicate active feeding. These properties resemble the infinity galaxy collision zone, scaled up to higher masses and luminosities. Some early quasars also show evidence of recent major mergers. Their host galaxies display disturbed morphologies and tidal features. This aligns with the collision-triggered direct collapse scenario. The same violent merger that built the galaxy might have birthed the black hole powering its quasar. Astronomers are now searching for heavy seed candidates in the early universe using Webb's deep field observations. They look for compact X-ray sources associated with merging galaxies. They search for unusual emission line ratios indicating recently formed black holes. They analyze velocity fields for signatures of direct collapse. Several candidates have emerged. One X-ray source at redshift 8 sits between two merging proto-galaxies. Another shows spectroscopic features consistent with a newborn black hole. A third displays the turbulent ionization pattern seen in the infinity galaxy. None are confirmed yet, but they're promising targets for follow-up study. If direct collapse commonly occurred in the early universe, it would explain not just the massive quasar black holes, but also the correlation between black hole mass and galaxy mass. Galaxies and their central black holes seem to evolve together. Their masses are tightly related. This correlation suggests they formed or grew through connected processes. Direct collapse during galaxy formation and mergers naturally creates this correlation. The same events that build galaxies through gas accretion and mergers also trigger black hole formation and growth. Galaxy and black hole grow in tandem because they're both fed by major mergers. The infinity galaxy demonstrates this coevolution in action. The quasar connection transforms direct collapse from a theoretical curiosity into a crucial component of cosmic structure formation. It's not just about explaining a few weird black holes, it's about understanding how galaxies and black holes grow together across cosmic history. The infinity galaxy forces us to rethink everything we thought we knew about black hole formation. The rules we wrote, based on nearby galaxies and computer simulations, don't capture the full picture. Nature found shortcuts we didn't anticipate, pathways we didn't include in our models. The universe is more creative than our theories. For decades, astrophysics taught a simple story. Black holes form when massive stars die. Small black holes grow slowly through accretion. Mergers combine black holes into larger ones. Over billions of years, this process builds the supermassive black holes at galaxy centers. It's gradual, predictable, and linear. The story made sense. The observations fit until they didn't. The James Webb Space Telescope keeps finding black holes that shouldn't exist. Too massive, too early, too bright. The simple story fails. Either we're missing something fundamental about black hole growth rates, or black holes have an additional formation pathway we didn't know about. Direct collapse represents that second pathway. The discovery that direct collapse can occur in metal-enriched gas through collision-triggered turbulence rewrites the rules. Direct collapse isn't limited to the early universe. It isn't restricted to pristine primordial gas. It can happen wherever sufficiently violent conditions arise. Galaxy collisions throughout cosmic history might produce heavy seeds. The process is ongoing. This changes our understanding of black hole demographics. Instead of one population with one formation pathway, there might be two populations with distinct origins. Light seeds from stellar death evolve into intermediate mass black holes and eventually contribute to supermassive black holes through mergers. Heavy seeds from direct collapse start massive and grow rapidly. Both populations coexist, mixing through galaxy mergers. Observationally, this predicts we should find black holes in unusual locations, not just at galaxy centers where mergers and accretion concentrate them, but also scattered through galaxy halos and in the space between colliding galaxies. Wandering black holes that formed during ancient collisions and never settled into stable positions. The Infinity Galaxy might be the first of many such discoveries. The rules change for galaxy evolution too. Black holes don't just passively sit at galaxy centers. They influence star formation through their radiation and jets. A heavy seed forming in a collision zone can suppress star formation across thousands of light years. This feedback affects how efficiently colliding galaxies convert gas into stars. The presence or absence of direct collapse might determine whether mergers trigger starbursts or quench star formation. The rules change for gravitational wave astronomy. Colliding supermassive black holes emit gravitational waves detectable across cosmic distances. Future space-based gravitational wave observatories will map black hole mergers throughout the universe. If direct collapse is common, many detected mergers will involve heavy seeds. The mass distribution of merging black holes will reflect two formation pathways. This provides a way to test direct collapse theory through gravitational wave observations. The rules change for cosmology. Black hole formation affects galaxy formation. Galaxy formation affects cosmic structure formation. Direct collapse alters the timeline of how structures grow in the expanding universe. Computer simulations of cosmic evolution need to include collision-triggered direct collapse to match observations. The parameter space of cosmological models expands. The rules change for planetary science in a surprising way. Black holes regulate galaxy-scale star formation. Star formation determines planet formation opportunities. The existence of habitable planets might depend partly on black hole formation history. More heavy seeds means more feedback suppressing star formation in some regions while triggering it in others. The distribution of life-bearing worlds could be influenced by processes operating on million light-year scales. But we're still at the beginning of understanding these rewritten rules. The Infinity Galaxy is one data point, one example, one observation. Science requires multiple independent confirmations before accepting new ideas fully. The team published their findings as a candidate direct collapse black hole, not a definitive detection. Follow-up observations continue. Webb will observe the Infinity Galaxy again with different instruments to measure additional properties. The Atacama Large Millimeter Array will map the cold molecular gas to see if any remains in the collision zone. Future X-ray missions will study the black hole's feeding patterns over time. Each observation either strengthens or weakens the direct collapse interpretation. Other teams are searching for similar systems. They're examining galaxy merger simulations to predict which collisions should produce direct collapse. They're developing new observation strategies to identify heavy seed candidates. The hunt is on for the second, third, and fourth examples of collision-triggered direct collapse. If the infinity galaxy stands alone as a unique accident, direct collapse remains an interesting possibility, but not a major factor in cosmic history. If more examples emerge, it becomes a fundamental process requiring inclusion in every model of black hole and galaxy evolution. The next few years of observations will determine which scenario is correct, but regardless of how common direct collapse proves to be, the infinity galaxy has already rewritten the rules. It demonstrated that black holes can form in places and ways we didn't expect. It showed that violent collisions can recreate early universe conditions. It proved nature still has surprises waiting in archived telescope data. The universe just taught us humility. We thought we understood black hole formation. We thought the rules were settled. We were wrong. The rules are still being written, and nature holds the pen.